Hello everyone, welcome to uh, week 3 lecture 5 of the software security course. So in this lecture we will be looking at the x86 instructions. So a brief recap of what we had looked previously, right? So in the previous lecture we had looked at the previous two lectures we had looked at in depth into what was linking and all those stuff, the L format, different types of linking, static linking versus dynamic linking, the advantages with each type of linking, how the shared libraries are being used, and how it, especially in dynamic linking, and how using shared libraries and with dynamic linking, it reduced the memory usage of an application, right? By having the same copy of the library in your physical memory, but maintaining but uh, instead of having duplicate copies when you do it in static linking, right? So these concepts we had looked into, and followed by that we had started looking into the x86 assembly language, the x86 assembly language. So basically, as far as the CPU is concerned, the assembly is the true programming language, right? So and with respect to an assembly language, three main things are there. So one is the instructions, the registers that it needs to access, and the memory. And when we take the instructions and registers, this is usually part defined by the ISA documentation. And the ISA acts, there are many different types of ISA, x86 ISA, ARM ISA, like that. And the ISA acts like an interface, like a reference, which indicates all the instructions, possible instructions that a processor supports. And the compiler engineer basically should refer to this ISA and write the compiler in such a way that all the languages, C or C++, Java, all those languages get compiled and converted, transformed into the assembly language following that specific ISA if it has to properly execute on that particular CPU, right? And as far as when we look at the assembly language, we looked at the overview of an assembly language. Basically, we looked at right. So basically, we looked at what the different assembly language, the different components are present in an assembly language. Specifically, we looked at the instruction, the directives, labels, components, etc. Right. So these are the various components, right? So if I want to define a section or something, right, where like the code should be placed or my data has to be placed, I basically should use a directive called dot section followed by the name of the section dot text, right? And if I want to follow some string or uh, some constant value, I basically will specify the directive, that command, right? So it directs that this particular value is a string or is of type long. So that's what directive is for, right? And followed by that you have label. So label is something which at runtime points to some particular location in your code file. Okay. And we looked at the various components in assembly, and one important component is the registers, and we looked at why we need registers and the different types of registers as far as x86 is concerned, specifically the general purpose registers. And also we looked at especially x86 registers support this notion of partial register access, where owing to legacy reasons and for compatibility with legacy code bases, right? Accessing you can access a 64-bit register as a whole, right? Just like that, or you can access the initial 32 bits, right? The partially you can access the 16 bits or 8 bits, like that. And all this was meant to support especially the older versions of code which initially ran on the older x86 processors, which were in 64-bit, were 16-bit, 32-bit architectures, right? So all those codes should also still be executable in this latest 64-bit processors that Intel is releasing nowadays, right, over the past few years. So for that reason, this partial register access is present especially in x86 ISA. It mandates this as part of the ISA documentation. So this was like the quick recap of what we had looked in the previous lecture. So in this lecture we will be looking at the various instructions that x86 provides, especially the basic instructions to get you started to understand any code base. And x86 is sort of like a pretty dense ISA, as in it contains lots of instructions, more than I guess 300, 250, 300 instructions, right? And usually out of that 300 instructions, only like 50 instructions or so like it are frequently used by the compiler engineers also. So say for example you write a C code, and if you look at the object dump of any particular C code, right, you take randomly any C code, say for example you take a browser or something, and if you look at the object dump to notice how many different instructions are being used out of those 300 instructions that any Intel processor supports, if you look at all the different instructions, the unique instructions that is present in that object dump, you will find at most like 50 instructions or so which are being used out of that 300, or even less actually, 30 or 40. So this is what so to understand an ISA, the basic concepts of an ISA, all the instructions, right, you need not go through all, you need not know all 300 instructions. Instead, just to you should understand like how do you perform a looping construct, right? How do you perform branches, if else branch, and how do you perform load and store to memory, adding, subtraction, multiplication. So once you understand those basic things, string manipulation instructions, it sort of becomes very trivial, and the other instructions on a case by case basis you can look at, refer to the manual and search it, right? So as far as uh, the main component in assembly is the instructions, right? So any instruction if you take in, um, you take in this x86 ISA, right, it usually follows a machine code format. So basically when we say a machine code format, it should be like understandable by the processor, right? So by the underlying processor, basically if you write some instruction, right, the ISA instructions, right, it should be something in a machine understandable format. So that's what, like you mentioned it as machine code format. Okay, so any instruction basically consists of these following components. So the name of the instruction, or we name it as the opcode, right, the name of the instruction, followed by the operands of the instruction. So operand 1, operand 2, right? So basically when we look at the different instructions, right, this will be the general format. So there will be an opcode, okay, and there will be two operands, and these two operands are sort of optional. So what I mean by optional is it can have one operand, it can have two operands, or it need not have any operand. So 0 or more operands. So basically operands are data values or any piece of storage, or right, on which the instruction computes. So if I want to add two numbers or something, I should pass those two numbers as operands basically to the instruction, right? So that is what operands are, the values on which the instruction executes or operates on. And the opcode is sort of special, and it denotes the and it denotes what the processor will um, sort of how the processor interprets the instruction, right? So when I tell the processor to add or subtract or something, each of that instruction will be assigned a unique opcode, and the hardware, the processor, on seeing a specific instruction, say for example I have an opcode, add is given an opcode of 0 1, and subtraction is given an opcode 0 2, right? So my machine code instruction will have a format like, which starts with 0 1 something, then the processor on seeing this, it identifies it's an add instruction, and it adds the numbers, right? And if it say like if it starts with 0 to something like that, then the processor on seeing this specific instruction 0 to, it internally it knows that it's a subtraction instruction. It subtracts the operands. So basically the opcode uniquely sort of identifies each instruction or each variant of instruction to be specific, and this opcode along with the operands, right, is all part of the machine code format. Okay. And the mission code format, so basically when you look at any object dump file, for example, if you look at any object dump file, for example this specific instruction B801, right? So for example this specific instruction at line 1167, right? So there's this instruction called move AX comma 0x1, and this move instruction in particular, the opcode of this move instruction is 0xb8. So the object dump file basically contains only this specific, the assembly file, right? Whatever you emit, the compiler emits the a.out file, it basically just contains only the second column values, 55, 57, 56, all these hexadecimal values, and this is being passed to the processor. So when it reaches line 1167, it looks at this specific value and it sees that it's value B8, and it identifies that this specific instruction is a move instruction, and all these extra numbers present after B8, these values represent the operands being passed, the type of operands being passed, and all those stuff, right? And so this is basically, so it identifies it's a move operation, and if you notice we have some value being passed to to a register, right? So those values and those registers, everything is sort of part of the mission code format. Am I audible now? Can anyone confirm? Hello, am I audible? Am I audible now? Can check your headphone or something. Hello? Am I audible now? Okay. So let's resume. And right. So we looked at we looked at basically the machine code format. So if you take an instruction, the format which is understandable by the processor is we have an opcode which uniquely identifies each specific instruction, and followed by that the various operands on which it should operate. Okay. So the opcode is something which is sort of internally defined to each processor, and for x86 ISA, so if you look at for example there is this website uh, called I'll share the link to this website, right? So we have this website felixcloutier.com, and so basically these are sort of all the core instructions as part of the x86 ISA. So if you see, there are all these instructions. and all these instructions are present. And say if I want to look at a specific instruction called move, right, or say the add instruction, right. So if you look at the add instruction, there is this opcode called there is, you see like the opcodes and all the details of that instruction. So this is what an x86 instruction would look like. So we looked at the machine code format. We have the opcode and the various operands. But what does the instruction operate on? What are the operands? Right? What are the possible operands? Should it be sort of like constant values, or what are basically are the operands in an x86 instruction? So as far as the x86 ISA is concerned, the operands can be of any of these three types. Am I audible? Hello? Right, okay, cool. So in that case, let's continue. Okay, so we looked at the opcode and which identifies each instruction, and followed by that each instruction will have 0, 1 or 2 operands, operand 1 and operand 2, and these are sort of optional. So it can, an instruction can have 0 operands, 1 operand or 2 operands, right? So but basically what are these operands actually? Okay, so if you take any instruction, it can have as operands a register or a memory location which is present in your RAM, or it can have an immediate value, a constant value. So these are all the possible operands that an instruction can operate on. So registers, it can be any of these 16 the general purpose registers, right? So all these registers we looked into in the previous lecture, RAX, RBX, RCX, all these 16 registers, right? So all these 16 registers are all uh, can be used in the instruction, right? All these registers can be an operand, or you can directly use refer to any memory location present in your RAM. So basically, if I want to say access address 0x 8000 or something, which is a valid location pointing to some address in your in your physical RAM, right? So, 0x 80,000 in your virtual memory, right? So in your virtual memory, so any valid address, right? So you can pass any location and access it, okay? And or else, so basically when the instruction will not compute on this value, instead it will sort of refer to the memory and get the contents present at the specific address 8000 and operate on that value which was present at address 8000. So that's what I mean by memory operands. Or if the operands are registers, it basically computes, say for example I'm passing an operand RBX register, it basically means it computes the value which is being stored in that particular register RBX, and memory operand, it computes on the value stored in that particular address location in the memory region. So in this case everything is like virtual memory, and so it looks up the page table and all those stuff like internal to the OS. It looks at that address 8000 and finds out um, finds out what the value is and computes directly on that value. If none of these are there, then the third option available to passing operands is directly as a constant. So you can just specify the value what you want to use in your instruction. Say if I want to add two for to a value to a register, right? So if I have some value in my register, like RAX register has the value 4, and if I want to add plus 5, right? So basically I can place this 5 as a constant. Since I know the value is sort of like a constant, I want to add 5, it's not going to change, right? I can place this constant directly as an operand, okay, and I can place it like 0x5. So what usually happens is, in your mission code format, along with your opcode, which identifies what instruction the processor has to execute, the operand 1 and operand 2 basically contains information with respect to which operand it is referring to. Okay, so for example, if it's accessing some register operand, so basically if it needs to access a register and get the value from the register, the operand 1 will have a separate encoding. So it will have some encoding like a different encoding, and say if it has um, the second operand is actually like an immediate field or something, the encoding will be different. So basically by encoding I tell the mission code format will be different, okay, based on which operand it's trying to use, right? And any instruction if you take in x86, the instruction how it works will be same, but as in like if you take an add instruction, the add instruction, the logic will be to add two numbers, but which two numbers it will add depends on what operands it passes, right? So it can pass a register as one operand and an immediate as another operand, right? Or it can pass a register and a memory. So basically what it will do is, it will take a memory location value present at that location and add it to the value contained within your register. So the operands what are being passed can vary to the same instruction, the add instruction, right? And to get a better understanding of this, right? So let's look at different instructions and see and see their corresponding um, op codes and all those stuff, right? So for example, uh, the first category of instructions that we would be looking into are the data manipulation instructions. So data manipulation as in all your load and store to memory, or moving value from one register to another, from one location to another, right? These are all data manipulation instructions. So you have this very common instruction called as the move instruction, which will be like pretty common, okay? So move instruction is basically it takes two operands. It takes two operands. One is the source and the destination, and whatever value is present in your source operand, right? The source is just basically copied into your destination operand. And note that by telling it copies from the source operand into destination, right? It can be any set of operands. So what I mean by that is, basically I can have a move instruction which takes, say I can specify a register RAX, and I can specify a memory location like this 0x8000. So basically it means the value present at this address location 8000 in the memory is copied into the register RAX. I can have vice versa. So the value present in the register RAX is copied into the memory location at 0x8000. Okay. Or it can be like a constant also. So move RAX comma some constant 0x5. So basically the constant 5 is being copied into the register RAX. So this is what I mean. The logic of move instruction is to copy the source operand into destination operand, but the operands what it's operating on can vary, and generally x86 ISA supports three different kinds of operands. It can either be uh, a memory operand, so you can directly access that memory location and get the value, or It can be a register operand. It can access the register and get the value, or it can be a immediate, a constant value, right? And based on the combination of operands which it uses, right, the encoding, the machine code encoding will change. So what I mean by machine code encoding is the representation of that instruction will change. So for example, let's look at the move instruction, right? So if you look at the manual of x86, you have so many instructions, and specifically I want the move instruction. So move over here. So this particular, the normal move instruction, right? So if you look at the move instruction, okay, you see that there is a table, and you in this table there are like multiple columns, and you specifically have to concentrate on the first two columns and the final column, right? The opcode column, instruction column, and the description. So if you notice over here, the opcode specifies the encoding, the specific uh, it's tied to that specific instruction. So initially I had mentioned in my previous slide, the opcode uniquely identifies each instruction. To be specific, right, the opcode identifies each variant of the instruction. Even if it's like the same instruction, it sort of identifies the distinguishes between different variants of the instruction. What I mean by variance is depending on the operands being used, right? So operand 1, so when we look at this move instruction, the operand 1 in the first case was a register RAX, but in the second case it was a memory operand where it was trying to access a memory location. So the operand 1 is sort of differing from in these two cases, right? And in the third case, I'm using a constant in an immediate value instead of accessing a register or a memory location. So to support, for the processor to distinguish between all these different types of operands that an instruction can support, right? The opcode will sort of contain all this information. So if you notice over here, for example, the first column, the first row, right? It mentions opcode 88, and instruction is move r/m8 comma r8. So basically what this means, how do we read this specific column, is that the move instruction has the following opcode 88, right? And the first operand can either be a register or a memory location, and this memory location, M specifies memory location, R specifies register, right? And it can either be a register or a memory location, the operand, the first operand, the operand 2, and followed by that the memory location specifically should be a location containing just um, 8 bits, right? So M8 is basically 8 bits, and that's your destination operand. So move is actually move destination operand comma source operand. So from the source you are copying into your destination value, the destination operand, right? So my destination is basically a register or a memory location which points to an 8-bit value. That's what we mean by M8. And the source operand should be a register, and that register should be a 8-bit register. So basically, when we look at the partial register access, we looked at the fact that in order to access register, the first 8 bits of a register, for example RAX, right? If you look at this the table, it will be a bit easy, right? So when we have to say the first row accumulator RAX register, when I have to access the lower byte or the second byte, so basically first just the 8 bits of the register, I can directly mention it as AL or AH. So the register R8, basically the source operand of my move instruction, should be AL or AH, and the destination can be any memory location or some register. So if you look at the description, it specifies the same logic whatever I mentioned, moving a 8-bit register value to some register or a memory location, and the size of that memory location, whatever that address is pointing to, should be an 8-bit size. So for this specific type of instruction where the destination operand is a register or an 8-bit memory operand, and my source operand is a 8-bit register. So for this specific move instruction, the opcode is 88, right? Now if you notice at the third and fourth columns over here, right? So here it specifies moving a 16-bit register to another register or a memory location, or moving a 32-bit value from a register to a memory location, and both of these are given a opcode value of 89, right? So similarly, if you take any other variant of the instructions, right? Like any different combination of operands, moving from moving an immediate value to a register or anything, it will have sort of a different opcode and encoding in order to communicate with the processor, to specify um, to convey to the processor that what type of operands the processor should operate on, with respect to the move instruction. So whether it should access the memory or the register, or it's been given a constant value, right? So if we want an immediate value to be passed, so if you look at this specific row over here, right? So the opcode starts with the value B8, and if you look at this specific instruction, it's basically I'm passing a constant value. Immediate 32 is basically a constant value which is of 32 bit size, and I'm passing that value to a register which is of 32 bit size. So for example, the move EAX comma 0x5, right? So that is an example which will have the opcode starting with B8. So like that, based on the operands being used in the instruction and the instruction itself, the opcode will be changing slightly. Okay, and so all this logic is encoded as part of your processor design. So so if you wonder like what is present in your processor, the transistors, all those things, what does it actually do is it basically like gets all the binary information, as in all this values passed to it, right? And it sort of parses those instructions and looks at each instruction. So if it starts with a B8 and something, it notices that it's a move instruction. It should move some constant value to a register or to some memory location. So the processor logic as a whole, this is what the primary logic of a processor, right? It has all these encodings within it, like a table. It stores it, and whenever you try to execute an instruction, it looks up these encodings and figures out what to do with that instruction. What does the user want the processor to do with those instructions, it finds out, right? So if you look at a real life code base, uh, look at this specific instruction, right? Move ECX comma EBX. Okay, so it starts with the opcode value 89, D9. So let's look at it. So basically I want to move, ECX is a 32-bit register, EBX is also a 32-bit register. So I'm moving a value in EBX into the register ECX, line 1168. So let's look at the table opcode. So I want to move from a 32-bit register into another 32-bit register. So this specific column should suffice, I guess, or this specific column. So any of these columns, right? So if we look at the opcode present over here, it basically specifies the opcode is 89 plus 89, right? So that's the first column, basically specifies your opcode, right? So if you look at the opcode 89 over here, yeah, this specific opcode. Yeah. So this specific opcode over here, right? 89 specifies it moving a 32-bit register value into some other 32-bit register value or a memory location. So that's what it's present over here, the opcode 89. And the following number D9, it's basically specifies which specific registers I'm using. So ECX or EBX register, all those stuff is sort of like encoded within this numerical value D9. Okay, and if you look at the previous instruction, right, move EAX comma 0x1. So if you look at the move instruction corresponding to immediate values, that is copying one immediate value into a register. So if you look at this specific value, so I'm basically trying to move some immediate value into a 32-bit register EAX, right? So this the specific instruction. So I'm moving an immediate value of 32 bits. So even though the value is 0x1, just one, right? It's interpreted as a 32-bit constant value, and is being moved into a register of size 32 bits, the EAX register. And if you notice the opcode for this specific type of move instruction, having the destination as a register operand and the source operand to be the immediate operand, the opcode is the B8. Uh, B8 is the opcode, right? And if you look at this, the instruction also, you have the opcode as B8 only, right? And if you look at the following values specified over here, followed by B8, you notice that there is this long value like 0, 0, 0, 0, 0, 1. So basically what this means is um, the part of this instruction, right? So I mentioned the instruction machine code format basically contains the opcode and followed by that the operands. So when we looked at the instruction move ECX comma EBX, we have the opcode 89, and this D9 specifies which register is the destination and which is the source register, the source operand and the destination operand. So similarly, this specific value over here specifies the source and the destination operand. And over here, my source operand is a constant value or a immediate value. So what does it matter? Like, what's the difference between the register and the constant value is? A register is basically like you have to access the register and get the value, whereas if you are having a constant value in your instruction, that value itself is sort of encoded as part of your instruction. So basically this highlighted part over here, right, it basically means it is this value 0x1, right? So for example, if you look at this specific instruction, move ESI comma 0x80E68A0. So this is like a proper 32-bit value, a constant value being moved into a register called ESI. Okay, sorry for the interruption. 1 second. Hello? Okay. A meeting room. Ah, okay. Ah. Yeah, sorry for the interruption. Right, so if you look at this specific instruction called the move ESI comma 0x80, right? So the first value sort of corresponds to the opcode, right? The first two values are sort of that. And if you look at this specific set of values, right? This specific set of values, if you just reverse the bytes, right? So it's written like A0680E08. So if I basically reverse it, so it basically it's 08 0E 68A0. So it basically corresponds to this value corresponds to this value present in your instruction. That is the constant value. So the constant value, that immediate value, is basically part of your instruction encoding itself. And usually, like accessing, if it's present in your instruction itself, right? It's faster to compute. So like not that much faster, like usually like in not even nanoseconds, much more like smaller delays, right? So this what is the difference between values present in the register compared to present as a constant, right? So if it's present in a register, basically you should store that value in a register and then access the register value. But if I know for sure what that value is, right, I can just encode it in a as an immediate value, and that value will basically be present in your instruction itself, right? At that in the memory itself, this value will be hard coded within the instruction. So this is what I mean by a constant value. And if you wonder why this uh, value is sort of like in reverse, and why not it's like after C6, why not it is like 80 E6, sorry, why not it's like 08 0868A0, as in like why the reverse is there, why not in the proper way, is because x86 uh, ISA usually follow something called as the Little Indian format. So basically the Little Indian format is your least significant byte, your LSB, right? So by least significant byte I mean this specific byte, right? A0 in this instruction, in this value, right? The most significant byte is 08 and my least significant byte is A0. So my least significant byte will be stored at the lower address, and my most significant byte would be stored at the higher address. Right. So if you look at this specific instruction move ESI comma that value 32-bit immediate constant value, it is the instruction is present at the address 8049 E4F, and this address is in sort of increasing order, right? So at 8049 E4F, the size of this specific instruction, this whole move ESI comma that 32-bit value instruction, takes around like 6 bytes. So each pair of each number, C7 is 1 byte, C6 is 1 byte. So it takes around 6 bytes. So if you add 6 to 4F, right, it's basically like 55, right? So it takes around 6 bytes, and out of these 6 bytes, the first 2 bytes denote the ESI instruction, ESI register operand and the move instruction, and followed by that is your 32-bit value of 4 bytes. And since my least significant byte is stored in the lower address, so the lower address over here is 4F, so C7 is at 4F, C6 is at 50 address, and the lower address 51 will store the least significant byte, which is A0. So the number is sort of stored in the reverse way actually. So in your lower address you will have your least significant byte, and followed by that it will be your the higher address, it will be your most significant byte. So this type of storing of values or constants in memory, right? My least significant byte in the lower address is sort of called as the Little Indian format. The opposite of this is will be your Big Indian format, where instead of A0 being present over here, the notation will be like 08 0E68, like that, the opposite of this, right? So basically at the lower address my most significant byte will be present, but usually Intel sort of follows this Little Indian notation. So don't get confused when you look at constants or something in future classes, right? In whenever you look at the memory dump, basically when you look at the contents of the memory being stored at runtime, you will sort of be looking at this sort of like reverse values, right? So you should start look at it in the reverse direction. So starting from here, you should look at from right to left, right? So that's what you should do. So you should not get confused. So you should keep this in mind. It's following a Little Indian format. So the whole 32-bit value is encoded as part of the x86 instruction as a constant value, right? So this is what is the core, the crux of how x86 instructions work, right? You have your opcode, and then you have 0, 1 or 2 operands, and the instruction encoding basically specifies two things, right? What instruction you are using, the processor needs to execute, it's a move instruction or something, and what are the operands the instruction has to execute on, the processor has to operate on, right? Whether it should access the register at a constant value, which is part of the instruction encoding itself, or it should access some memory location, get the value, and use it for computation. So all these different types of operands basically should be the processor. It should basically be like you should communicate with the processor, and the opcode contains all this information, all these minute details. The opcode will contain, and the processor will look at the opcode and identify which instruction and where are the operands located in a register or some memory location. Right. So, any doubts till now? So, once if you understand what the different operands can be, and how to just have a understand at least the first two columns of this table and the last column, right? So basically R is register, R16 means it's a 16-bit register, M32 means it's a memory location, and that specific address should point to a memory location having a 32-bit value, right? And IMM means it's basically a constant or immediate value. And these numbers 8, 64, 32 is basically the size of that value in bits. So once if you learn to understand what this table does, right, you can basically go ahead and understand all these different x86 instructions easily, right? So if you look at the beneath this table, there is this description, like a detailed description, which sort of specifies like what are all the like corner cases, the actual logic which is present in the processor, right? All those instructions, that logic will be present as part of the description. So if you look at this operation over here, this operation text, so this basically is the logic which the processor is um, coded with. So the hardware, right? The hardware basically contains this logic within it. So basically, it will sort of do all these checks in between, all these logic. It will compute whenever it has to perform a move instruction, something like that. So understanding the different types of operand and how each instruction supports these different types of operand is crucial to understanding the ISA, right? So any doubts in this specific move instruction, the how the operands were being used? Okay, so excuse me. So in that case, let's quickly go through all the other instructions, right? So you will come across these instruction called the exchange instruction. So basically the exchange instruction sort of swaps the values, right? So it will swap the destination 1 and destination 2. So if it's present, say if I'm having something like exchange RAX comma RBX. So if RAX initially had 5 and RBX had 6, it will basically contain, after this operation, it will contain 6, and this will contain 5, right? And once this is done, you basically can sort of, so this is what your exchange instruction does. So now if you just look at the manual, right? So even for this exchange instruction, you can see that it supports different operands. So it can support, if you look at this column, right, this row over here, it basically tells that it can be, one operand can be a register operand, the other can be a memory location, and both are of 16-bit size. If you want the same with 32-bit size, that also it supports. So the opcode varies accordingly, based on the operands which are being used with respect to that exchange instruction, right? So every instruction from now on, whatever instruction we sort of come across, right? These instructions will most probably support the register. It can take as operands any register or a memory location or a constant value. But some instructions will have some restrictions. Uh, just a second. Recording Vinay or Lale. So there will be a restriction. So for example, if we look at this, oops. So if you look at the exchange instruction in particular, you will notice that there is no encoding with respect to an immediate value. So if you notice all the rows, like the destination and the source operand, both will be either a memory location or a register location, and it won't be a you cannot find an immediate value. So just intuitively speaking, right? If I want to swap locations, swap the values present in two, destination 1 and destination 2, I cannot swap and store something in a immediate value. So that's like part of the instruction itself. It's encoded. It doesn't point to some storage location like a register or a memory location, right? So intuitively speaking, so the exchange instruction won't support the immediate value operand. So these type of restrictions or like conditions will be there. So you should sort of refer to this manual, right? Like just have a quick glance and you'll easily get to know that the exchange instruction doesn't support any immediate value, right? So like this, for every x86 instruction, there will be a corresponding entry in this website, right? And so this is the exchange instruction. And coming to the push and pop instructions, these are sort of like specific instructions. So specific as in the previous cases, right? I specified what my, for example, in the move instruction, I specified the two operands that the move instruction has to operate on, the source and the destination operand. Explicitly, I specified these two operands. By explicitly as in like operand 1 should be this particular register, like that I specified it explicitly, and that information will be encoded within your instruction opcode, right? What the number of that register, the first, second, or out of those 16 registers, which register is the operand 1, which register is operand 2. If it's a memory location, what's the value of that memory location? All those things will be sort of encoded in the instruction. But some instructions use the concept of something called implicit operands. So basically, by just using that instruction, you will be passing some operand to that instruction. For example, this push instruction over here, you can specify a value something over here, the source operand. You can specify the source operand, right? This source operand will be pushed onto the stack memory. So we'll be looking at the stack memory in detail in tomorrow's lecture. But just assume that stacked memory is some memory location specified, right? And what this means is, and the hardware sort of knows where the stack is located, the stack memory is located, right? So basically, the location where the stack memory is located is sort of stored in a register called RSP. So this RSP is nothing but stack pointer. So if you look at the list of registers that x86 supports, you have this register in this specific row, right, called stack pointer. RSP, ESP, all these different variants, and everything is sort of like a stack pointer, right? So when you look at the push and the pop instruction, it basically either, if you have taken a data structures class, you will be learning a data structure called a stack data structure, which sort of follows uh, an order of um, the access order is basically LIFO, which is last in first out. right? So for example, if I have some memory like this, so basically how a stack will work is, if I am pushing some value, for example, uh, uh, let's say these are the list of values 0, 1, 5, 6, 7, right? These are the list of values, and I'm pushing it in this order starting from 0. So basically what happens, I'm first pushing 0. 0 gets stored at the uh, bottom, and basically there will be a pointer called as the stack pointer. So let me name it as SP, right? The stack pointer. And basically the stack pointer will tell what's the sort of the unfilled position of the stack. So basically the stack pointer will tell from which position I should start filling up the stack, right? That is, it points to the top of the stack. It points to the top of the stack, and beneath that SP everything is sort of filled up, right? So now 0 is filled up, and now when I want to push 1, right? So 1 gets pushed, and my SP sort of, my stack pointer gets incremented over here, right? And now when I push 5, 5 gets pushed, and then 6, and then 7. And in every operation of the push operation, my stack pointer gets sort of um, incremented, right? The value gets updated accordingly. And what happens finally is the stack pointer now points to this specific location over here, right? And now this is basically like I'm inserting into a stack. It basically inserts in this manner. So everything, it's sort of uses the stack pointer and inserts at the top of the stack, right? It uses the stack pointer and inserts at the top. Now I want to retrieve the elements from the stack. So basically retrieving is, you will be doing the opposite operation called as the pop operation, right? So when I do like pop from the stack, my stack pointer sort of now gets decremented. So now my stack pointer won't be over here. Instead it will be decremented, and the value present at the top, right, the value 7, that gets removed from the stack, popped out from the stack. So this gets sort of popped out, 7, right? And similarly again when I do a pop operation, 6 gets popped out. So when I want to get the bottommost value in the stack, which is the 0, oops, which is value 0, right? This value if I need to get, I should pop all these elements 6, 5 and 1, and then only get 0. So basically the stack is sort of follows this access logic called last in first out, right? So whatever went last, right, that comes out first. So in my case 7 was pushed last, but when I do a pop instruction 7 comes out first, right? So this sort of um, data structure which supports this last in first out access mechanism is the stack data structure. And the stack data structure is sort of has like many applications, and in tomorrow's lecture we'll be looking in detail something called as the call stack. Basically when you have a function, right, when you write a C function like function main, you do some operation and then you call some function called f1, and then you just close the main function, right? So basically the main function has to call the function f1, and after f1 computes, it returns back to the remaining part of the main function. So how does the processor sort of keep track of, okay, currently I'm in main function, the function f1 is being called, my control should basically go and execute the f1 function instructions, and after executing all those instructions I should return back to the main function and start and resume execution where like as in after the call to f1, right? the remaining portion of instructions in the main function should be executed. So all this, how does the processor keep track of? Excuse me. So all this is maintained via this call stack mechanism, right? And the data structure that it uses is the stack data structure. It supports this last in first out access, right? And basically, if you notice, whenever I want to push a value into the stack, I'm changing the stack pointer, which sort of acts as the a pointer which is pointing to the top of the stack, until which location my stack has been filled, and where I should pop the element or where I should push the elements, the stack pointer denotes, right? So x86 instruction by default supports a concept of stack memory, where we have these instructions called push and pop. And the push and pop basically has this logic. So push instruction followed by an operand, source operand, specifies that the source operand gets pushed into the stack, and where is my stack located, where is that memory located, right? So that memory is basically located at some location. I should push it into the stack memory. And where should I push it? If you notice in the example that we saw, I should push it into a location pointed by my stack pointer, because the stack pointer is sort of location pointing to the top of the stack, which is yet to be filled up, right? So the x86 ISA has this register called stack pointer, and it implicitly, whenever I use this push instruction, right, it implicitly looks at the stack pointer value, right, the stack pointer register, and that register, say if it has RSP has some value like 0x9000, right? So the 9000 denotes the location at which the top of the stack is said to be filled up. So it basically copies that source operand, whatever that value is, right? Whether it's a register or some immediate value, something. It basically pushes that value in this location pointed by the stack, and it modifies the stack pointer such that it now denotes the new top of the stack. So here basically in x86 ISA, it decrements the stack pointer. So when I say it decrements the stack pointer, the if you take this as your stack memory, my stack memory will sort of, this is the higher address. So say this is 0x9000 and this is 0x8000, right? This will be the starting of the stack. This will be where my RSP will be pointed to, and when I am pushing some value like 5 onto the stack, 5 gets pushed and my RSP sort of gets decremented. So now it will be 0x8 C, I guess, right? So this will be the value of the stack pointer, right? And now again, if I do a push instruction, the stack pointer will still decrease. So basically my stack is growing downwards. Downwards as in, the starting from a higher memory address, it sort of grows towards a lower memory address, right? And when you look at the notion of the how the process layout is present, right? So if you notice, um, right, so if you notice over here in this particular slide, I had mentioned higher memory address and lower address, and the stack I have placed an arrow like sort of growing downwards. So this basically this the actual understanding, right? Your stack pointer initially will be at a higher memory address, and on every push instruction it sort of grows in a downwards direction. That is, it sort of keeps on decrementing, right? So decrementing, you should not take it in the actual sense of like reducing memory space, but the order in which your stack grows determines whether the memory address, the stack pointer, is incremented or decremented when a push operation occurs. So basically, if you just take the reverse, as in my stack is located at 0x8000. So for example, if I take the opposite, um, sorry for the scrolling. So basically if I take the opposite, right? So if I take the opposite where stack starts from 0x8000 and can keep on going. So in that case, I push some value 5 and my stack should be incremented by 4, 0x8004. So the order in which my stack grows, whether it grows towards higher memory region or lower memory region, sort of specifies whether my stack pointer gets incremented or decremented. So here, in as far as x86 is concerned, it assumes the stack grows from a higher region, higher memory address to a lower memory address. So what it does is it pushes the value, right, the source value into the stack register, into the stack location, which is pointed by the register RSP and decrements the RSP value. And the pop instruction sort of does the opposite. The pop instruction basically, it takes that value present at the location pointed by the stack pointer register, gets that value and copies it into the destination operand. So the destination can either be a register or some memory operand anything, and it increments the stack pointer. So it sort of removes that element from the stack. So note that by removing means I'm not zeroing out the element. So for example, if I want to pop out this value 5, right, the pop instructions does not replace this 5 by some dummy value or some 0. Instead what it does is it just sort of retains the 5 as it is, but it changes the RSP alone back to 9000, right? So basically now when I want to sort of again do a push instruction, this 5 gets overwritten by a new value. Okay, so this sort of like a small catch point that you should understand, that when you pop a value from the stack, you pop something from a location pointed by the stack pointer register. It's in other case you don't zero out a value, you just sort of like move that value from that stack location to the destination operand, but that value in that stack location at 0x8 FFC is sort of still remains as it is, but you just increment the stack pointer, and in a future instruction, in some future time, when you push something onto the stack, this particular value will be overwritten, right? And over here in both the push and pop instructions, the implicit operand is the stack pointer register. So if you notice in both of these instructions, we would not have mentioned RSP anywhere, right? So the hardware basically by default looks at the stack pointer register, RSP register, and uses that to find out from where it should pop the value or to where it should push the value, right, in the where the stack memory is actually present, and decrements and increments that value. I didn't understand your question. So what chipset is being used is? Can you be specific? I sort of didn't understand. So basically all this logic, right? This increment, lower and store, whatever. So when it looks at push source instruction, the hardware logic basically, the logic is sort of encoded in the hardware, right? The processor has this logic within it that when it sees a push instruction, it will take that value, see the stack pointer value, access that specific memory location, copy the value, the source value into that memory location, and decrement the stack pointer register. Exactly. So the processor, your x86 chip, right? The physical chip, that chip has the logic encoded within it. And when I tell the instruction executes, right, it basically executes on that chip. So the ISA everything is sort of acts as a reference to what all instructions that specific microprocessor can support or can understand and execute properly. And for it to execute all these instructions, it supports all these different opcodes. As in, when it looks at opcode, say, for example, in exchange instruction, when it looks at opcode 90 and followed by this, right? It basically understands that it's an exchange instruction where the destination is an AX register and the other is some register of 16 bits, right? When it's looking at some other opcode like 86, it understands it's an exchange instruction but a different set of operands. One is a memory and the other is a register operand. So all this logic is sort of encoded within your microprocessor, the hardware. Your physical hardware has all this logic. So does this answer your query? Yeah, cool. So, so just imagine, right? So when we tell x86 just like an extra bit of information, there are like different categories, types of ISA, and generally they can be categorized into like two types of ISA. One is called as a CISC and the other is called as a RISC ISA. CISC ISA is, the full form is no, so basically, like when we tell an ISA, a processor supports an ISA, you sort of, it should support all those instructions present in that ISA. Right. So it can be any x86 processor, i7, i3, i5. All these microprocessors, all these processors will sort of support all most of these instructions, right? And just you have all these instructions, right? Around I guess 300 instructions or something. So even if I minimize the page, it sort of goes into these many instructions, right? And if you notice, some instructions over here are specific to the Xeon processor, I guess. And if you notice, some are sort of uh, some specific instructions, right? So the processor logic should, the processor designing, right? When we tell um, chip designers or processor designers, they basically should have all this, design the processor and encode all this logic, support for all these 300 plus instructions into your microprocessor. So just imagine how difficult it is to support all these instructions, right? Given the constraint that the processor should be sort of like at nano scale, right? Nowadays it's like 2 nanometer technology, right? And also the power consumption. So each time when you execute an instruction, the processor has to look at the opcode, look at the operands, figure out what operands it has to use, and then access the memory and all those stuff. So for all this, the processor has to consume energy, right? All this information, this opcode specifies to this specific instruction, the combination of operands, all this stuff sort of complicates your processor design. And Intel, as far as it concerned, the x86 ISA, the ISA is called as the CISC ISA, as in complex instruction set architecture, complex ISA, right? Compared to x86, if you look at some other ISA called as a ARM processors, which you will be using in your mobile phones, right? The Snapdragon Qualcomm processors, all those processors support an ISA called as the ARM ISA. The ARM ISA follows a notion, a design strategy where it's following a RISC type of design. It's called as a reduced instruction set architecture. So it basically will not have sort of like 300 instructions to support. It will just have like maximum 100 instructions, something like that. So the advantage is that the less number of instructions the processor has to support, the more simpler it logic, you can simplify the logic of the processor. So the chip designing and all those stuff becomes easier, and also power consumption and all those um, uh, things you need not worry about very explicitly. It sort of simplifies your design a lot, right? So, but Intel, for some reason, they sort of ventured into this type of ISA design, which is complex ISA design, where you have this more than 300 plus instructions to for the processor to support. Okay? And if you try to understand the internals of an x86 processor, it will be sort of like complex and difficult to implement an x86 processor on your own, because you have to support all these instructions for you to support the x86 ISA completely, right? Uh, this just like a bit of background information, right? So given this slide, we were looking at all the various instructions. So we looked at the common data manipulation instructions. So we have this move instruction, the exchange, push and pop are specific to the location pointed by the stack pointer register, which is taken as an implicit operand, right? So these four instructions are sort of very crucial when we have to understand data manipulation instructions. Now let us quickly look at what various arithmetic operations can be possible in x86 ISA. Right? So you have the add instruction, which basically takes two operands, and it takes the source operand and the destination operand, and a destination doubles up as a result operand also. So basically destination is equal to destination plus source, right? So if I have like add RAX comma RBX, so it basically means, say 5 is present in RAX and 6 is present in RBX register. So you add 6 to 5 and the value of RAX is now 11, right? So this is what arithmetic instructions are all about. Similarly, for the add, similar to that, you have the subtract instruction, right? And the other two instructions are increment and decrement, which adds one or decreases by one. And if you notice, it just takes one operand alone, right? Because you know for sure it adds or decrements by one, subtracts one, and this one logic, this adding and the subtracting one, this logic, everything is encoded as part of your processor, right? And you have an instruction called neg instruction. So neg is negate instruction. It just negates your operand value. So if you are passing some negative number, it makes it into a positive, negates it, or some positive, it turns it into a negative number, adds a minus sign to it, a negation sign, right? And notice that I have specified the logic of what the each of the instruction does. Destination equal to destination plus source in the case of add instruction. You have the increment and all these stuff. But what operands it can support? It can support all the three operands. It can either support a register, a memory operand, or an immediate value. So if you look at the x86 manual again, so the key point whenever you become a security engineer, right, you should be, or even like a normal software engineer, you should be able to easily look at these type of references and try to understand what these references actually mean, right? It will be sort of like confusing. So for example, if you ask me what these rex and id all stand for, even I'm not pretty sure, but you should have the spirit to google it out and like find out um, what those mean when the situation pops up, right? So in that case, this is the add instruction. If you notice, it supports adding a immediate value to a register, or adding uh, immediate value to a memory operand. All these different types of operands, the add, subtract, negate, increment, all these instructions support uh, implicit. All these different type of operands, the arithmetic instructions support. Okay. So any doubts in arithmetic instructions until this? Uh, we shall discuss compare now. But before that, before moving to the compare instruction, any doubts in these add, subtract, increment, decrement, and all those stuff? So you have instructions like multiply and divide. I would share links to it as in the resources section, which sort of you can look it up and understand how the multiply instruction and division instruction works. Right? So basically, multiplication and division. An important thing is similar to how your push and pop instructions implicitly access the stack pointer register RSP. Your multiply and divide instructions will implicitly access some specific registers. So this is like a small exercise. I will leave it to you. I will share the link to both these instructions. You can have a look at these instructions and find out what the multiply and divide instruction logic is, like what the operands are and what are the implicitly accessed operands, right? And coming to compare instruction, the compare is sort of a very interesting instruction, and this you should understand this compare instruction clearly to understand how control flow will work, right? So till now we looked at arithmetic and data manipulation instructions, but we never looked at any instruction which allows you to call a function or to perform some if-else condition. Like for example, if I have a code like if I less than 0, do something, else do something. So this is not um, so based on this condition over here, I less than 0 or not, my instruction execution should either execute this or this, right? So basically this sort of like a control flow construct. My control flow, instead of going in a sequential way, it sort of gets interrupted in between. So either the first part or the second part, both should not execute together. Right? So this type of instruction we have not yet come across. So we will see at that instruction, but before understanding those control flow instructions, we should understand how a comparison, this I less than 0 or something, how does this comparison takes place, right? So you can have so if you want to compare, right, you basically have less than or greater than, right? These are like the two common comparison schemes. Or you will have equal to, and other variants are less than equal to or greater than equal to. Right. So basically what x86 does is it sort of has one instruction to support all these different comparisons, which is my compare instruction CMP. So the compare instruction, what it does, it takes two operands, the source 1 and source 2, right? It does not write to any register value. It doesn't write explicitly to any of these register source 1 or source 2, right? Notice how it's being named. That's very important. If you know if you look at add destination comma source instruction, by looking at the naming you can understand to this operand some value is being written, right? The sum of source plus destination operand is written back into the destination operand TST, right? But over here, if you notice compare instruction, both are named as source operands, right? Because to none of these operands, whatever is being passed to the compare instruction, I am not changing its value. I'm not writing any value to both of these operands. So that's why I'm mentioning it as source 1 and source 2. So none of these are destination operands, right? And what the compare instruction does is it basically compares source 1 and source 2. And what does it compare is that it compares, what it does is it just uh, does this computation source 1 minus source 2. It just subtracts source 1 minus source 2. And based on this subtraction, right, you can infer multiple results. Say for example, I have source 1 and source 2, and let's assume let us like draw a column, like a table, right? Different values of source 1 and source 2, and what is source 1 minus source 2. So if I just have a column and say this is 6 and this is 4, source 1 minus source 2 is 2. If it's 4 and 6, it is minus 2. If it's 4 and 4, it is 0. Right? So these are the different values that source 1 and source 2 can have as in different conditions. So basically any computation, any subtraction you take, it can both can be equal or both can be different. In case if it's different, it can either be greater than or lesser than, right? So you get one case the result is a positive number, the other case the result is a negative number, and in final case the result is 0. Right? So three different cases you get. Now what x86 does is it sets something called as the status flag register. Right? So there is a register, like a sort of a special register called as a status flag register, which is E flags. And this E flag register is of 32-bit or 64-bit based on the ISA you're using. And this register, in this register there are sort of each bit in that register has a different meaning. So if you take for example the E flags register, each bit or a set of bits in this E flags register, so starting from 0 till 31 bits, each set of bits will be corresponding to some specific flag, and three important flags are there. One is called as the zero flag, ZF, other is the overflow flag, and the other is the sign flag. Right? So basically, based on the value what I get from source 1 minus source 2, the processor implicitly, right, implicitly sets the flags in this E flags register. So when I do 6 minus 4, it takes a sign, it sees the value as 2 and it doesn't set anything. So basically the sign flag, what it means is if it's a negative number, it is set to 1. And the overflow flag is if it overflows, right? Basically when it overflows in addition, when you add two huge numbers and when it overflows, you cannot still contain it within your register, right? Then it sets to 1. And the zero flag is when my computation result is 0, right? Then it sets to 1. Okay, so when I get a positive number, it doesn't set any of these flags, right? So basically my E flags is 0. When it gets a negative number as result, it sets the sign flag to 1. And when it gets a result as 0, it sets the 0 flag to 1. The processor implicitly sets all these flags to 1, the corresponding flag to 1. So this is what happens in a compare instruction. So it takes two operands, source 1 and source 2, subtracts these two operands, and based on the result it gets, it sort of sets some flags implicitly, and these flags sort of indicates what the result is, whether it's a negative or a positive or it's a 0 value, which indicates that the source operands were equal, right? And what's the big deal in this, right? By setting these flags, what can you infer from this? When you do this compare instruction, and when you see that the sign flag is set to 1, it basically means source 1 minus source 2 is a negative number. And what does it infer? What can you infer about the operands from this observation is that my source 1 is lesser than source 2. Then only it results in a condition where source 1 minus source 2 is a negative number, right? So basically a negative number indicates source 1 less than source 2. A non-negative number indicates source 1 greater than source 2. And 0 value indicates source 1 is equal to source 2. So just by subtracting two numbers, the two operands, and setting the corresponding flags and observing whether it's a 0, positive or negative number, you basically you basically infer whether which operand is greater than the other operand and whether they are equal or not. So you can infer this comparison whether it's greater or equal to lesser than by basically subtracting source 1 minus source 2 and setting the corresponding flags. Now why are these flag register is being set implicitly is because we have to use that this comparison result, right? So if you notice in compare instruction, I mentioned that you don't write the result whether it's greater than or less than or equal to. You don't write it explicitly into the source or source 1 or source 2 operand. Then where should I store the result in? How will my processor remember that result? It remembers it in the E flags register. So it sets that flags implicitly in this register, and within that register flag, one specific bit is the 0 flag, one specific bit like the second bit or fourth bit, it corresponds to the overflow flag like that. And now this E flags register will be used in what we call as the um, conditional branch instructions, right? So these conditional branch instructions, so when we look at the C language, like if I less than 0, right? So if A less than B, let's keep it like that, right? You do some logic, else you do some logic, right? So how this will be converted into assembly is, first I should do this comparison. So it will compare A comma B, right? And what it does is this comparison gets stored in the E flags register, right? And assume the start of this if condition code is present at some address called 0x8000, and the else code is present at address 0x9000. So what it will do is, using this E flags register, the comparison result is stored in this E flags register, and now I can use any of these conditional branch instructions. So basically when you look at this conditional branch instruction, you have all these different sets, right? So J stands for jump if, and the next to JE is equal, A is above, B is below, G is greater, L is lower. Okay, and whether it supports signed or unsigned, right? Whether it sees it as a signed number or a unsigned comparison, right? That it So basically if I mean JE instruction, the JE instruction is jump if it's equal to, if it's JA means jump if above, JB is jump if below. So jump if below, jump if above, what should be above, what should be below is exactly what is being stored in my E flags register. So basically if I want to have this A less than B comparison, and based on this comparison I should jump to the instruction, means I can use this instruction called jump if below. So basically I can have um, jump if jump if greater. So it's the opposite, right? So jump if greater 0x9000, okay? And this is the if part, if code, and at 0x9000 you will be having the else code. So how a control flow instruction basically works is, x86 supports these different instructions, okay? Jump equal to, jump above, jump below, jump greater, jump less than, everything. basically what it means is my the previous I should have performed a previous compare instruction, okay, compare source 1 source 2, and it should have set the E flags register. Now my jump instruction, the conditional branch instruction, will look at the E flags register and see whether the sign flag is set to 1 or 0, whether my 0 flag is set to 1 or 0. So my if the 0 flag is set to 1, it means both the operands A and B were equal. So it means A equal to B, right? So in that case, um, what it does is it sort of looks at that logic, and if I'm using say this jump equal to JE instruction, the first instruction, right, JE address, it basically means if the 0 flag is set, right, in the last compare instruction, the result of that compare instruction is stored in the E flags register, and in that register if my 0 flag is set, it means both the operands are equal, and in that case, the condition satisfies equal to condition, and it jumps, the control flow jumps to the address which is specified as the operand over here, right? And here over here we are in our example we are using this instruction called jump if greater than. So jump if greater than is basically JG address over here, right? So JG address, it means jump if greater than destination less than source. So what it says is in my last compare instruction, I will look at the sign flag and the 0 flag and like host of other flags, and based on that the processor infers whether the A is greater than B or A is less than B. Now if A is greater than B, right? Then in the case, what happens is this condition A less than B is false, right? So if A is greater, so sorry, so it should be actually J greater than or equal to. So like it basically is the opposite of, what's the opposite of A less than B? The opposite is A greater than or equal to B. So basically I check for this condition, right? I check whether A is greater than or equal to B in this specific condition, J greater than or equal to E. If this condition is true, right, A greater than or equal to B, it means I should execute my else code. If A is less than B, I should execute the if code. So that's what I'm using in this instruction over here, J greater than or equal to E. So I'm passing a compare instruction and values are A and B, and it sets the E flags register. This E flags register is implicitly used by my jump greater than or equal to instruction JGE, and if based on seeing those flags, right, whether the sign flag is set to 0, my 0 flag is set to 0, it denotes that A is greater than B, or if my 0 flag is set to 1 and the sign flag is set to 0, it denotes A equal to B. So in both the cases it means A is greater than or equal to B. And if this is true, my if condition should not be executed, so I jump to this address 9000, and which is where my else code is present. If this condition is not satisfied, it won't jump and it will continue execution, which is what the if code is present, right? So this is how the conditional branch control flow instructions take place in x86. So you don't sort of the x86 ISA splits the comparison from the conditional branch, the actual control flow instruction. So my comparison instruction takes place separately, and you implicitly store that result in your E flags register, which is used by your conditional branch instruction to infer whether it's greater than or lesser than or equal to, and based on that it jumps the control flow changes based on that condition, right? And x86 ISA supports all these different types of conditional branch instructions, which is jump if equal to, jump less than, jump below than, all these different types of conditional instructions x86 supports. Okay, so any queries in the compare instruction and how these conditional branch instructions execute? Okay, cool. So if I just say if I'm reversing this condition, instead of if a less than b, say if I have if a greater than b, then basically my instruction will change. It won't be JGE, instead it will be JLE, right? So basically, instead of I'm checking whether to execute my else condition, what should be my clause? It should be a less than or equal to b. So based on this if condition, if I change from a less than b to a greater than b, the instruction JGE also changes correspondingly to JLE, right? So this is how my conditional branch instruction gets inserted along with the compare instruction. So we looked at conditional branch, compare, data manipulation, and arithmetic instructions. Now you would have sort of seen some instructions called some constructs in your C language. For example, say you have a main function, right, and you will have a loop for I less than 0, say infinite loop, and then within it you have a break condition, right? So this break is something called unconditional. So it doesn't check whether I less than 0 or I greater than 0, nothing. When it looks at the break, sorry, when it looks at the break statement, without checking any condition, it sort of breaks the loop and exits out of the loop. So these are called as unconditional control flow. And in x86 ISA, there are these instructions which are called unconditional branches. So when you come across these instructions, these instructions don't refer to the E flags register or something. Instead, it sort of just directly changes the control flow, right? So there is this call address, right? So this call address is basically, if you notice the logic, so call and return, we will look into depth when we look at call stack tomorrow, right? But and syscall will also look at it tomorrow, right? So this is something to be discussed in detail. But look at this specific instruction, jump address. So the conditional branch instructions were of the type, they look at the E flags register and see whether it's greater than or lesser than, look at the flags and infer these observations, right? Infer these results and then jump if it's true or false, right? But unconditional branch is sort of, if it's like JMP 0x9000, after executing that instruction, it jumps to 9000 address. It doesn't check for any flags register or something, right? So basically your exit or your return instruction or anything will be transformed into this particular instructions called jump address instruction, right? And your function calls everything, the return function, return function call, so return 5 or something. In x86 there are specific instructions called um, represented by call and ret. Okay, so we'll look at call and ret tomorrow in detail, because understanding call and ret is pretty crucial to understand these software exploits, right? It's tied to how your call stack operates. Okay, so this is unconditional branches, and quickly going to logical instructions, which is basically operating on Boolean values, similar to your add and subtract, right? You have these instructions and, or, XOR, not, and all those things. Okay, so the working is pretty same, and this destination gets returned to, and what gets added, it's the destination and source operand. And again, it can take either register, memory, or immediate values, similar for the other logical instructions. And one specific instruction is the test instruction. It tests whether source 1 and source 2, it tests whether it's equal or not or something like that, and it sets the status flag. So the test instruction is sort of similar to your compare instruction, but the compare instruction does a subtraction, the test doesn't do a subtraction, instead it does something different. But both of them set your status flags, right? And you can use either the compare or test instruction based on the logic of your code, right? You can use either of these two, and next immediately after that test or compare, you can use your conditional branch instruction like jump if greater than or jump if equal to use that e flags register and do a conditional control flow jump. So these are all the high level overview of the different set of instructions that are present in x86 ISA, right? And the other instructions, sort of miscellaneous instructions, is the NOP instruction and load effective address. So LEA means load effective address. So you would have come across in your C code, for example, you would have like int star C. You are declaring a pointer, and uh, you have to initialize this pointer to some address value. Say you are having some integer int b, and you have storing the address of this integer in the variable C pointer. So it's basically you use the ampersand, right, to get the address of b. Okay, and the address is being stored in this specific variable C. So this address of, right, this basically is represented in x86 ISA using load effective address. Okay, LEA instruction. So if you have some instruction like LEA uh, RAX comma something like this, some source operand, what it does is it computes the address whatever it has to access from the memory, but doesn't access the location in that memory, right? Doesn't access the address location. Instead, that address value alone, just like that, the address value gets copied into the register RAX or some destination operand. So this is what load effective address is all about. So you will see many instances of LEA instruction in your object dump. It's sort of like very commonly used instruction, right? And one common use case is this ampersand operator in C, right? You want to get the address of a variable where it is being stored. You use this instruction LEA. And then there is this famous NOP instruction. So NOP is basically no operation. So it does nothing. Okay. And why do we have a NOP instruction in the first place? Is there are many use cases. Uh, Say for example, you have some application code base. Okay. So even in security arena, you have, say, you have written an application. Okay, this application is having some browser logic within it, accessing the internet and all those stuff. But suddenly you find out there is a security exploit present in your application. Okay, so basically what happens is you have to patch this exploit. So you have to apply a patch to this exploit in order to mitigate. The mitigation is to apply some patches. But you notice, right, the object dump file, or basically your a.out file, will basically just have all these hexadecimal values, the instructions, and you won't be able to understand these values. And also if you change one value over here, for example, if I just add 0e over here, it means it's overwriting the next value present over here, 83. And when I change at the hexa level, all these values are crucial for the processor to execute properly. For example, at line 1180, that value 83 specifies the opcode of the AND instruction. If I change that value, if I want to insert new instructions in between to patch my exploit, I should basically overwrite. I cannot overwrite these instructions, the AND instruction. Then how shall I patch the executable? I cannot pass a new executable because the user again has to download and install these executables and all those stuff. Then what should we do? right? What's one particular solution to this is to add something called as NOP instructions in between, wherever you feel it is necessary, you feel that a patch might be applied in future. What I can do is I can add NOP instructions like this. So basically what happens is, when during my processor execution, after executing this move instruction, when it sees this NOP instruction, it just bypasses this instruction, as in it does nothing. It just wastes one cycle or something like that, right? Uh, it it executes the NOP instruction but won't affect your registers or memory location, nothing, no logic, right? And what you can do is, when you want to patch your application with some mitigation, with some solution to prevent this exploit from being used by the attacker, right? Uh, you can replace these NOP instructions with something useful like add 1 comma 2, something like that. So basically your NOP instructions act as code placeholders in the future, where you can remove those NOP instructions and place your other instructions. What you can add your code into those by replacing those NOP instructions. Okay, and there are many other use cases of NOP instructions. One common use case is this, from a security perspective or from a software patching perspective, where you can insert NOP instructions at some places within your code, so that in future when I want to add some extra logic or I want to mitigate some exploit, I can replace those knobs with some actual instruction which does some logic. So with this, right, we sort of have covered all the basic instructions that that you need to understand uh, to fully appreciate x86 ISA, and um, to get started, not fully understand, to get started with x86 ISA and to get understanding of your object dump file, right? There will be many other instructions that you will come across in your object dump file based on the binaries that we work on, for example SHL or something. So I will share the x86 that website documentation. You should basically look into that documentation and find out what that instruction does or something, or you can just basically Google it also. Both will help out. Okay. So in tomorrow's lecture, we will look at specifically how my call stack works, the syscall instruction, how the call stack is maintained by the processor, how does function calls operate on uh, modern x86 processors. Okay. Any doubts till now? Any queries in any of the instructions that we covered? Okay, cool. Thanks so much. Um, okay. I'm not sure how to pronounce that. Sorry. Right. Thank you so much for attending the class. Let's meet tomorrow.